So hello everyone, welcome to Basic Chemistry Plus, and today we are going to go for the oxidation state. Don't forget to like, share and subscribe to the channel because this topic is very important in terms of our board examinations. So the oxidation state of the D and F block elements, and this is a pretty anomalous properties we see in the oxidation states of these type of elements. So we are going to learn first what is an oxidation state. So over here you can see that oxidation state is nothing but an arbitrary concept. So actually there is no such real reason behind this concept, but this concept helps us to find out a lot of things. So it is just a this is like valency, not exactly valency. It is like valency. So let's just understand what do I mean over here. So when you think about oxidation state, it is trying to tell you the amount of, in this chapter, I'm talking about completely in D block elements, the amount of electrons donated by the metals. So over here, we are going to talk about the metals and the number of electrons they can donate during a chemical reaction. That is called their oxidation state. So let's just have a look into the large variety of oxidation state of the transition metals over here. You can see all of them have more than one oxidation state, and there is a lot of them. So first over here you can see the variable oxidation state is seen because of the participation of N minus D and NS orbital. So both the N minus D and NS, they work as the valence cell. So for scandium, if I see 3D1 4s2, right? 3D 4s, 3D comes before 4s, isn't it? So 3D1 4s2, 21. So just crisscross. Okay, one goes to T3D and S goes to. So now over here, NS electrons, there are two electrons, right, for NS. So scandium 2 plus is stable with a 3D1 configuration. But still, if you just think about it, 3D1 is not that stable electronic configuration. So scandium 2 plus is more stable in 3D3 configuration. I mean 3D0 configuration, where scandium 3 plus is there. Right. So the thing is, the 4s2 electrons, that is the reason first that goes out, and then the 3d1 electron goes out as well. Together they make this plus 3 oxidation state. Remember, scandium is the only one who is very stable as plus 3 oxidation state for the first transition series element. Okay. Now over here, if I just move on to the next point over here, you can see that the lowest oxidation state is found because of the ns orbitals. So ns orbitals means you can see that ns2 is the general electronic configuration we see over here, right? So because of this ns orbital, there are two electrons. That's why the plus 2 oxidation state, which is the lowest oxidation state, is found over there. And except the scandium, as I already told you, plus 2 is the most stable configuration. Okay, 3D orbital is getting more and more stable. Okay, so plus 2 is the most stable orbital configuration because of the 4s2. Other than scandium for that 3D1, that also goes out, right? So that's the concept over here. So for scandium, it is plus 3. Okay. Now I would move on to the next point over here. Yeah, point number 4. So you can see over here the first few elements, they shows less oxidation state only because of the s orbitals. So as I told you, the lower oxidation state is being seen because of the s orbitals over here. Plus 2 oxidation state. Manganese shows a variation of oxidation state, a lot of variety of the oxidation state because of D and S, both of them are there. So for manganese, it's 3D5 4s2. So there are a lot of oxidation state you can see. If the 4s electron goes out, then you would get plus 2 oxidation state. If the 4s electron along with one 3d electron goes out, then we get plus 3, plus 7, plus 5. Plus 7, how do you get it? Well, when all the electrons are out, 3, 5 and 4s2, then you get and plus 2, how would you get it? Like from the 4s only. So this is how we get all these values over here. And similarly on the last few elements as well, we see less oxidation state because of their high nuclear charges. Okay. Now in plus 2 and plus 3 oxidation state, uh, the bonds formed essentially are ionic. So you know that because plus 2 and plus 2 oxidation state are easy to get. Okay, you can take out the electrons easily. That's why they are essentially ionic. But for the higher oxidation state, they are covalent. Okay, so over here you can see manganese has plus 7 oxidation state in KMnO4. Over here, if you just try to calculate the manganese oxidation state, it would be K plus MnO4 minus. First break it like this, it would be easier for you to find out. Then find out the oxidation state of manganese then. So it would be Mn 04. So it will be plus 7 only. This is how it looks like. Okay, this is having a unique hybridization as well. It's called SD3. It's a tetrahedral complex only, SD3. So all these bonds over here are covalent bonds. Okay, because manganese is in +7 oxidation state. So all of them are covalent. SD3 is the hybridization over here. Now over here you can see that within a group, the maximum oxidation state increases with the atomic number. So when your atomic number is increasing from top to bottom along the group, your oxidation state is increasing, because again, because of the electronic configuration you see. For iron this is +2 and +3, because look into the electronic configuration. First 4s electron goes out and then the 3d. But if you just go down, you can see the electronic configuration. So first 4s electron goes out, then what would happen? Then Fe2 plus would be 3d6. Is it stable? No, it is not. So again take out one more electron. Is it not stable? So take out one more electron to make it 3d5. Now it is stable. So Fe3 plus Fe2 plus, both of them are there. Now if you just look into ruthenium over here as well, there are some variable oxidation state. How are you getting +3? So over here you can see 5s, one electron from 5s, one electron and two electron from 4d. Let me show you. So over here 4d7 5s1 from ruthenium. So now if I show you +1 oxidation state, so it would be just 5s electron gone. So +1 oxidation state is there. Okay, is it stable? No, it is not. So what would happen is it would go to +3, because if it does, so 45, this is a stable configuration. That's why +3 is being seen over here. Okay, so this one and this, and all of them, if I just take all of them, it would be 8 electrons. So +8 would also be there if I take all of them out. So +3 +8 +7 is another intermediate oxidation state. For osmium this is +2, so because of the 6s electrons, +3 because of 6s plus 1 electron from 5d. Okay, so it would be 5d5 then if one electron goes out. That's how 5 +3. And how is it getting +8? All the electrons, sorry, 5d and 6s, both of them gives you +8 if all of them goes out. So these are the different processes. So you need to know the electronic configuration to make it easier for you. The transition metals are also formed compounds on low oxidation states with carbonyl ligand. So they form a low oxidation state with the carbonyl, like they are the sigma donor pi acceptor type of ligand. So that was there in coordination chemistry. So for metal, if you just react with carbonyl, so carbonyl gives it electrons to make a sigma bond, and metal becomes electronically higher, like electronically rich, so it donates the electron back to carbonyl to make a pi bond. So that's why we call it sigma donor pi acceptor. In these cases, metals can be seen in a lower oxidation state. Okay, sigma donor pi acceptor. We can see metal to have a lower oxidation state in these type of situations. Okay. So the next topic would be our standard electrode potential. So I would just keep this video up to this only. In the next topic, we will be moving on to the standard electrode potential, and this is a very important topic as well. So make sure you do watch the next video, do subscribe to the channel, and definitely watch the previous videos as well. They are also important. I'm making short videos right now. The standard electrode potential, don't miss this out as well. So today I'll be just keeping this video up to this only. So see you soon. Bye everyone.